but some of this I think might be a little bit new too, or at least extensions of what you've already done. So we're gonna talk a little bit about intervals first of all. We just started talking about that yesterday a little bit. So one way to define an interval, we looked at some graphs at the end of the period yesterday. An interval is just a part of a number line without any breaks. Okay, plain and simple. That's it. That's an interval. What do you suppose, without staring up here for a second, what do you think the difference between a finite interval and an infinite interval would be?
Like an infinite interval,
Say it again.
like look at like something that's like greater than 2.
Okay, good. So it's only got either got no boundaries or only one boundary. So it's unbounded on at least one end, right? And then a finite interval, by contrast, would be like, yeah, it's got boundaries on both ends. Okay, good. So if an interval consists of all real numbers greater than or equal to 2, then we know what that looks like. Let's just take a real quick look at a couple things here. Different descriptions. Can you guys see that, or is that too small? Everybody see that okay? Yeah.
It's smaller than my ambitions.
What's that?
It is very small.
It is very small, I agree. If, here, maybe I can make it a little bigger. I think I can.
Sorry.
How's that? Is that better? Is that good? All right, so let's look at a couple different types of notation here. So if we're talking about a description of an interval where it's going to go from A to B, from the number A to the number number B, sorry, and it's including both of those, right? Then one way that we are probably pretty comfortable with writing that is like this, as an inequality, right? Now, from last year, we talked a little bit about this. How do you say that? How would you read that inequality? Tyler.
X is greater than or equal to A, but less than or equal to B.
Okay, good. Maybe the one small tweak I'd make there is we want to include the word and instead of but. And that seems like I'm being pretty nitpicky there, but and is an important word in math. That's technically, we call that a conjunctive inequality. I won't write that down for now. I mean, just an and inequality is fine. That's two inequalities in one though, right? So that's a compound inequality. Writing it this way is important for a couple of reasons, but for our conversation right now, it's important because it looks just like that interval would look when it's graphed, doesn't it? Right? On the left, we've got the boundary A, and on the right, we've got the boundary B. Okay, so let's compare that to these other notations, and this is where I think this might be a little bit new to you. So if we write that as a set notation, we just started talking about that yesterday. For now, set notation is no big deal. I mean, it's going to look, what's the difference? Well, the only difference is we're going to include the set inside script brackets, because that's how we write sets. It means we're enclosing a bunch of values. And then all this is saying, remember, is just that for the variable is x such that, this is true, such that x is pinched between A and B inclusive, or such that x is greater than or equal to A and less than or equal to B. It's really almost the same as that, isn't it? Right? Just notationally a little bit different. That might seem like kind of, why would we do that? Well, notation's important in math. And I think, especially for a group like this, a very advanced math group that's going to be going on in math, I believe it's important to kind of get some exposure to the proper way to notate things in math. So that's how we'd write that if we wanted to use set notation. What about interval notation? It looks like, almost like an ordered pair, right? What do you think how are we going to think about interval notation? Can anybody take a stab at maybe why does it look like that? What's the anatomy of that interval notation? What do you think? Yes, Owen.
I mean, they're both the boundaries.
Okay, good. So we noticed that the left boundary is A, right boundary is B. That makes sense. What about the square brackets? What do you think, Sam?
It means it's including A.
Okay, good. Now, what would those brackets look like if maybe these weren't including the endpoints, if these were inequalities without equal signs? Parentheses, yeah. Here's how I remember that. It takes a little more ink to write a square bracket than a round bracket, and that's because it includes that extra point. Okay? Make sense? All right. Okay, what if we wanted to do something like all real numbers greater than a? Well, this makes sense, doesn't it? Then the inequality is just x is greater than a. If we write that as set notation, it's just a set of x such that x is greater than a. And then, what about this over here? Does that make sense? Talk to me about that. Kirk, what do you think about that? Why do you suppose we have that infinity there?
As long as it's bigger than A, it's
Okay, good, because we're saying it's bounded on the left at a, but on the right at infinity, but infinity's not a number, right? Right, we gotta be careful, and I do this all the time. We say there's an infinite number of things. You know, that's really not probably the best way to say it, because it almost implies that an infinite number is a number, and it's not, right? What does infinity really just mean? Yeah, unlimited or boundless, right? So, do you suppose I could put a square bracket on that end? Wouldn't make sense, would it? So whenever we talk about open intervals like that, and an open interval meaning that it's not closed off at the other end by a boundary, we always have to include a positive infinity if we're moving to the right, or if we're moving to the left, we'd go, does this make sense? If we want all real numbers less than or equal to a, then that means that a is going to be the right boundary, right? In this case, we are including a, so we need the square bracket, and then on the left end, we're unbounded, so we'd have to have that open bracket, right, and a negative infinity. Okay? Questions on that? I tell you what, I probably should tell you this too. If you don't want to write all this down, you don't have to, because this is literally something that you can access online. This is this very thing. This is your resource. I'm just kind of going through it with you, just to introduce you to it as much as anything. But you can go back and look at it the same time you want to. Oh, what else we got? I don't know. It's telling me. Oh, okay. How about that? Well, I didn't realize that was there. We talked about this yesterday. The vertical bar means such that. Okay, we kind of dealt with that. And then what else? Talked about that too. Guess we're good. Okay. So what about something like this then? Let's just try to, just a little practice here. Why don't you real quick in your notebook, just scratch that out of your own. Just write the 3 different kinds of notation for each of those different intervals. Has anybody started the homework? Okay. You did. How far did you get? Halfway, okay. What do we get here? Let's try this. What if we want to write these as inequalities? Luke, first, second, third, or fourth? First, good. Okay. How about this one? Which one? Second, good. All right, that's good. Okay, so we got those. Let's. So the set notation would just go right with that, right? Once you know how to write it as an inequality, you know how to write it as a set. That's no big deal. What about using interval notation? Let's see, Gabe, which one's this? Last one, okay. Good. And how about that guy? Looks good. All right. Table's complete. Looks good. Real quick, what about something like this? We'll just zip through these. So, which one of these, Lily, which one of those is going to represent that infinite interval?
Oh, me?
Yeah.
Oh, X is
First one, okay. What about this guy?
the last.
Last one, okay. Everybody see that? Questions on that? Good, I think we got this. Probably advance a little bit here. Interval notation. Katie, what do you think? Which one's that? Second one, good. That's good. Which one? Oh, yeah.
Okay.
Yep. Okay, that makes sense. All right, so let's move ahead a little bit. So we're okay. We got the idea of intervals, no big deal. We can express that using all three kinds of notation. Now let's maybe try doing this with looking at a graph. So a couple things just to remind you. I know you guys know this, but actually you tell me. Here, that's not. What is the domain? When we talk about the domain of a function, what is that? What's the domain? Matthew, you remember what the domain is? The x values, good. Okay, and generally for us it's x. It'd always be, we can associate the domain. In fact, I'm gonna write this down. It's kind of a good way to remember this. So the domain versus the range, right? What are those? Okay. The domain, these are both sets, right? The domain and the range are both sets of values. Domain would be the set of x values typically, right? Range would be the set of y values, okay? What if we're talking about it as input and output? Which one goes where? Input is x, good. What if we're talking about it as independent variable, independent variable? X would be the independent, okay? And the y would be the dependent, right? Okay, does that make sense? Here's one way to remember that. It doesn't work for independent, independent, but we usually don't use those anyway. We almost always talk about domains and ranges in terms of those quantities. D before R alphabetically, X before Y, I before O, right? Just a way to keep that straight, okay? And what about the range then? Oh, I actually talked about it. So the range is the output values, right? Okay. So input, we know a domain and range. The end behavior, this is a big deal. We talk about this a lot in calculus too. A lot of times in calculus, I'll talk about the tails of the function, and that means the end behavior. So that means what's happening way out there or way out there, right, typically. But when you, or if there's an endpoint, if you actually get to an endpoint, you know, you're talking about that, I suppose. Although that's really not what we're interested in. So consider the graph of this function below. Let's look at, oh, that's not linear. Well, I think we can't see this graph. That's a little weird. Okay. That's not gonna work. Let's just skip down here. Let's look at this one instead. We've got this function, kind of a weird function. F of x is an exponential function. F of x equals 3 to the x. So that's shown right here. Based on that graph, what can you tell me about the domain? What do you think? So the domain, that's the value, the input, right, or the x values. All the x values that work for this function, right? Every place where any value of x we could plug in. There's a couple ways you can look at this. We can look at the graph, or we can also take a look up here at the function, right? What are some things, what are some places in a function where an x value wouldn't work? Can you give me an example? What do you think? I heard something over there. Well, okay, zero's okay. Zero's a number, but sometimes zero can be dangerous. I'm not talking about this function here, but what if we had a different one? What if, I'm just gonna write one up here. What if we had a different function, g of x, that equaled something like 3 over x? Tyler, you have an idea? Okay, what's the problem there? Can't divide by 0. Okay, so that's one kind of place where a domain would have to be restricted, right? Because we can't divide by 0. That's one of the rules we talked about a little bit last year. We'll talk about it a lot more this year. There's two things we can't do for real numbers. We can't divide by 0. Remember what the other thing is? You can multiply by 0. That's fine to do. But dividing by 0 doesn't work. Okay, you can't take the square root of a negative number. In fact, you can't take any even root, and we'll talk a lot more about that this year. You can't take an even root of a negative number, a 4th root, a 6th root. But for now, just think of it as a square root. So if I had a function like this, what if I had h of x equals 3x times the square root of x minus 2? Now, this is a pretty advanced concept. I'm jumping ahead for you guys a little bit here, but can you identify maybe a place from looking at that function where we'd have some problems? Give me a value of x that would not work. 2, somebody said, 2 would actually be okay because that would give us the square root of 2 minus 2, which is 0. What is the square root of 0? 0. Okay, but 1 wouldn't work, would it? 1 wouldn't work because 1 would give us a negative number under there. Does that make sense? Okay. We'll come back later and we'll talk about maybe how we could take a function like this and actually write what the domain would be. But just for now, let's just understand, all I really want you to see at this point right here is that there are places sometimes where functions have to be restricted because of those two rules, right? Can't divide by 0, can't take an even root of a negative number. Okay, so looking at the function, actually let's look at the graph first. Does it seem like there's any values of x that aren't going to work? What do you think? Any ideas? Yeah, I don't care, just throw it, it doesn't have to be right. Let's just talk about this. What do you think? Based on that graph, do you think a value of x, think I could plug in -1,000,000? Seems like you could. That arrow indicates it's going backwards, right? presumably forever, okay? What about a number like 10? Okay, and the reason being, it looks like this thing is climbing pretty steeply, right? Okay, and the thinking, I'm just, tell me if this is right. The thinking is that as I move this way, this thing is just climbing more and more steeply, and so it's getting really, really high, right? Okay, but there's nothing to say, there's nothing that indicates up here that this thing ever becomes asymptotic, right? It's true. I mean, you could, and here's kind of the proof of that. Look at the, you know, remember asymptote, you know what that means in asymptote? You guys talked about asymptotes before? Oh, okay, I threw out a word that's new.
Yeah.
We'll get to that too. Asymptotes are like vertical boundaries that the function would never cross. It would just kind of push up against it and then just get higher and higher. There will be some cases, we'll look at some stuff like that soon, where we will have these vertical asymptotes, where the function just stops and it can't go beyond that. This one doesn't seem to have that though, and here's one way to prove that to yourself. Look at the function itself. F of x equals 3 to the x. It's a weird kind of function. We haven't dealt with exponential functions very much. But is there anything preventing me from putting in a trillion for x?
No.
There's not, is there? There is no upper limit to how big numbers can get. And so that's going to be an enormously large number. But if I evaluate this at a trillion, all I'm going to get is 3 to that big number.
You don't have to write it. Yeah.
You get the idea, right? I probably didn't put enough zeros, but you get the idea. Huge number. That number is staggeringly big in our universe. There's really nothing that we could think of that would approach that. I mean, the number of estimated atoms in the universe is 10 to the 8 when we observe the universe. That's way bigger than that. But it's a number. Mathematically, it's fine, right? So as we push out to the left, this function is just going to get ridiculously tall. Who cares? There's no limit, though. Does that make sense? Okay. So what should the domain be then, if we want to write an inequality? Which one? Okay, yeah, now there's another issue here we got to be really careful with. There's probably two candidates, right? Which are the two that we would potentially use? First and the third. Okay? Think about this for a second. In fact, turn to your neighbor and just take 10 seconds or 15 seconds and discuss that. See if you can come up with a conclusion. Which one of those, number 1 or number 3, is probably the right answer? No, it is not too early.
Okay, if you want to like space tangents again, I might volunteer.
Oh,
First period.
all right.
It doesn't help that usually when you're doing a
Yeah,
sentence,
true.
you drop all the lines, and so I'm like,
Slowly going. Ah, so the mind.
but then nothing for it to be equal, it's like kind of.
Okay, what do we think here?
Third.
Third one, okay. What's the difference? I mean, these look pretty similar. What's the big difference here? What do you think, Maisie? How come the third one is the right answer and that one doesn't make sense?
Because the top one has like it include both.
Yeah, less than or equal to? That doesn't make sense, right? Infinity? You can't equal infinity. So yeah, so it's this guy. Okay, so then set notation, well, which one's it gonna be? Bottom one, right? And interval notation, top one. Yeah, good, we got it, okay?
Every number greater than negative infinity and less than infinity.
Say it again.
Isn't every number greater than
Yeah.
infinity?
That's right. So now let's go back and look at this. So what's that mean about this domain? Is it restricted? No, it's unrestricted. What's another way of saying all these things? Well, here's another way we could write these. I mean, I don't want to, we're going to stick with this, But like later on in calculus, one thing we'll do is we could just say all reals. Same thing, right? The whole set of real numbers would work. Or we could say x is an element of the reals. Any real number. I'm not gonna do that to you now, but just see isn't it weird in math, there's all these different ways of saying the same thing. They all have their own little place. We'll stick with those three. How's that? Okay, what about the range? Let's go back and look at this graph. Now the range, which one do you think is harder to do, domain or range? Range, definitely. Domain you'll find is always gonna be a lot easier because you can just go up here and kind of look for those places where x would blow things up. Make you divide by 0. The range, you almost have to look at the graph. What do you think's going on there? So what do you suppose the smallest value that y could take is? No? Ah, very good. Okay, it's not actually 0, is it? This is another case where it's like, remember we've gone back to this a million times, if I cut my distance to the door in half, I don't ever get to the door, right? But the door is the limit of my motion, right? So it's gonna get pushing down against y equals 0, but never get there, right? What's the biggest number it could be? Yeah, I mean, it's unlimited, right? There is no bound in terms of the positive end, right? You can go as high as you want. So then what's that gonna look like in terms of an inequality? Oh, whoops. What's that gonna look like in terms of an inequality for the range? Yeah, everybody buy that? Third one?
Yeah.
Right? That works. Okay, so let's let's write that as, we'll set notation. That's a gimme. If you got the inequality, you got the set. Good. Interval notation. Last one. Good. And notice we got that rounded bracket on 0 because it doesn't include 0, right? 0 is just the boundary. Okay. So now here's another notation for this. This is how the arrows are important. We're starting to talk about this in more detail in calculus right now. This is how we start the year, is talking about the same kind of stuff, just at a little higher level. So which one of these do you suppose, which ones of these make sense? Let's just look at them one at a time. The way we would say this is, as x approaches 0, so the arrow makes sense, right? As x approaches 0, f of x, a fancy name for what? Y, approaches infinity. As x approaches 0, y approaches infinity. Is that true? No, it's not, is it? What's the answer there? As x approaches 0, what does y approach? 1, right? And it actually is 1, right? We would write, just so you can see this once, what we're doing in, in calculus right now would be to say, okay, a way of saying that is the limit of f of x as x approaches 0 is 1. We're talking about this exact thing in calculus right now, and that's what we'd be writing. So in a couple of years, you'll be seeing this again. Oops. Okay, so that one doesn't make sense. How about this one? As x approaches infinity, f of x approaches positive infinity. Does that work? See, show of hands. If you agree, raise your hand. That works. Okay, yeah, you're on the spot. You're on the spot. What do you think?
Well, like, the one that goes up is gonna be like a higher number, but the other one's still gonna be a higher number too, just not that high.
Okay,
They're not gonna be like at the same level of almost.
you're right. You're right. But there's still, Emma brings up a really good point. Probably the same thing a lot of people are thinking about. As x increases, y increases much more rapidly, right? But what's 5 times infinity? infinity, yeah, okay. What's infinity times infinity? Infinity, okay.
Still infinity then?
But that's a really good point, and actually, we'll talk, I don't wanna say too much about this right now, but we'll talk in calculus, once again, we'll talk in calculus about how you can actually ask the question, what happens if you're comparing two infinities? Can you get an answer? And sometimes you can't. Sometimes one of the infinities grows faster than the other, and you actually can get an answer. So it's a really good point. But for our point now, we're just looking at a graph. Wouldn't you agree that as x approaches infinity, which just means as we walk out the function to the right, as you know, forever, what's going to happen in the y direction? Well, it's obviously going to go up forever, isn't it? Does that make sense? So this is one that works. How about this one? As x approaches negative infinity, f of x approaches negative infinity.
No.
Does that work? As x approaches negative infinity, does y approach negative infinity? No. That one doesn't work. What should that be instead?
Yeah.
Right? As x approaches negative infinity, and think about it as an ant walking on the function. If the ant's going to walk in the x direction infinitely far, what is the ant's y value going to approach? 0, right? He's just going to walk ever and ever and ever and ever closer to the x-axis without ever touching it, right? Okay, so that's it. Okay. All right, so we'll skip that. There we are. Okay, graphing a function on a restricted domain. So sometimes domains are restricted because there are values of x that don't work, where the function blows up. Sometimes they're restricted because we restrict them, right? Sometimes, a lot of times, what's math good for? Well, I mean, I shouldn't say that, terrible thing to say. Math is good because it's just good. I mean, it's interesting because it works. But one of the hats I wear every day is a physics teacher. And when we talk about physics, that employs math to build models that make predictions for us, right? And so let's say we're doing something like we want to predict the height of an object that we're gonna launch in this room. It's gonna go up in the air and then come down at the floor, right? Well, mathematically, if we were to use the physics equations to predict the height of the projectile, it's gonna increase and increase and increase, and then it's gonna go down. And let's say the height of 0 is the floor. Well, mathematically, it wouldn't stop. Mathematically, it would just keep going to negative numbers, right? But the object doesn't burrow through the floor, right? And so you see that there's a place there where the mathematics stops applying to the real world. And so if we want the mathematics to only apply to the flight of the projectile, we want to limit it to only include the part where the height is positive, not where it's below the ground level, right? So sometimes we restrict things artificially because it makes sense for us, all right? So unless we state otherwise, we're going to pick the biggest domain the function can support, right? But sometimes that doesn't work, right? So, see that kind of that weird R with like the double, that means all real numbers, right? Instead of real numbers. So, unless otherwise stated, any line, because lines don't do anything weird, they're just straight, lines are going to have, there's no restriction on the domain, it'd be all real numbers. Sometimes, though, we do put restrictions. So let's look at an example. So how about if we take this function right here? That looks weird. That's not supposed to say fx. It's supposed to say f of x. I don't know why it looks that. But just pretend it says f of x. So what is that? F of x equals negative x minus 3. Describe that function to me, please. What's it look like? What's its shape? So it's a line, isn't it? It's mx plus b form. What's the slope? What's the y-intercept? So it's easy to graph or identify that line, correct? Okay. But notice there's another little piece of information here. It's with the domain, x is greater than -4. What's that going to do to the line, do you think?
It stops you at -4.
It stops it. Okay. So the line, the mathematical graph of this function is a line that goes forever in both directions. But because of this restricted domain, we're going to erase part of the line, right? It's going to be a linear function. The graph is a what? So it's a linear, it's going to be a ray this time, isn't it, right? Because we're erasing half of the line, so it's half the line. I mean, it's a portion of the line, right? With an endpoint at where? Those look kind of weird, but I don't just want an answer here, I want an explanation. An endpoint, they're looking for an ordered pair, right? An x and y value. Okay. Well, what's the x value of the endpoint going to be? -4, right? We know that because that's where the line stops, right? So we know then it's got to probably be, well, maybe one of those two. Which one makes sense? That one on top. Well, what's this f of -4? What's that business? Ah, that's a y value, isn't it? Right? Look at this here. If we've got, if f of x equals -x minus 3, what's f of 2? What does that notation mean? Yeah, it means we're going to plug a 2 in, right? We're evaluating the function at the x value of 2, right? And that's going to give us back the value -2 minus 3 equals -5, right? So in other words, another way of saying this is that when I plug 2 in for x, I'm getting back -5 for y. So that would be a point on the line. And maybe that's not included in our line. I guess it is actually. Yes, Kirk.
X being -4 is successful.
You're right. You're right. It can't be, but we're talking about an endpoint, right? Now, is that endpoint going to be solid or open? It's going to be open, so it doesn't actually exist there. It's an excellent question. It doesn't actually exist there, but it's still a really important point for us. It's like the door, right? When I'm walking towards the door, I never get there, but the door is still really important to our conversation, right? That's the only point I don't get to. It's the endpoint of my motion, right? Make sense? Okay. So this is it then, right? What is this value? Well, we could put it in and see, right? If we actually plug in, -4, we just get -4 minus 3 equals -7, right? And so this is really the very same thing as saying -4, -7. We just left it as f of -4 though, right? Yep.
Wouldn't it be positive because it's a -x, and then x is -4.
Oh, you're right. Yep, you're right. So it'd be, what, 1?
Yeah.
Okay. In fact, we can always write an ordered pair. If the function is f, if that's how we're defining y, then couldn't we always write an ordered pair as x, f of x? Same thing as xy, right? Okay. All right. Oops. Okay, we did that. What was it? 1? Yeah. So we got that. So if we look at the graph then, There it is. Right? You already told me earlier that the equation f of x equals, what was it again? I don't even remember. You told me it was a line, right? You told me it was a line with a y-intercept at -3 and a slope of -1. So there's our infinite line, but because of the restriction on the domain, we only draw the line in its domain. Okay? Okay, so what's the range? We'll probably have to look at the graph to get the range. Okay, good. Start the statement with x though. We're describing x. So what do you think? Madison, what do you think? How am I going to say that? If I start with x, how would I finish that? If I'm looking at the, I'm sorry, y, not x. I'm talking about the range, right? So what are the y values here? Looks like we're starting that value. No. So 1 down, right? So how do I say that? X is, yeah, there you go. Or why do I keep saying x? Y, talking about range. Y is less than 1, right? Okay. So right there, agree? Okay. All right. Let's see, skip that. How we doing? Are we getting close? 1 minute? Call it good. Okay, we just got one little other thing to look at, and then we're good. You can start on the assignment. Hey Jessica, I'd be willing to just. Here's what I want to do. I kind of want to shorten the assignment a little bit because it's seeming a little bit long. Not too bad, but I was going to cut a few problems out. I might post the other one and just you can do only the parts that you haven't done, and I'll just give you credit.
Okay.
Okay, so just remind me like when I'll just put in 100%. Okay.
Thank you.
Mm-hmm.
Is your, do you know if we're doing Friday straight?
Let's see, Friday, today's Wednesday. I'm gonna give you guys a little time to work tomorrow. So we'll probably just like go through a little bit of new stuff, but this is probably the biggest introduction to new stuff because it's the, from now on it'll be a little shorter pieces.
Okay.
I'll record it though, yeah. And it shouldn't be, it wouldn't be a problem because this thing we're going through, you can do the,
Yeah.
I'll put the video up, you can just do the lesson on your own, you'll be fine.
Oh.
Yeah.